Hi guys, welcome back to the channel. In this lecture, we are going to calculate the collapse load for this gable frame. Okay. So as you can see that this is a gable frame. Okay. There is one horizontal load is acting at this point B. Okay. One vertical load and one horizontal load is acting at point C. And there is one vertical load also for this member PC. Okay. So we need to calculate, and there is also a load of magnitude 2W acting on this member CD, right? And you can see that the plastic moment capacity of the columns are MP. Okay, this member, the plastic moment capacity is 1.5 MP, and for this member, the plastic moment capacity is 2 MP, right? And all the dimensions are given. So basically, we need to calculate the value of this W at the collapse. So at the collapse, we should have the sufficient number of plastic hinges. Okay, sufficient number of plastic hinges, or you can say mechanism should be there. Okay, so this is a gable frame, right? So basically, while calculating the collapse load, first step is basically to calculate what is the static indeterminacy of this frame. Okay, so this is basically a gable frame. Okay, so we need to calculate the static. First step is to calculate the static indeterminacy of this frame. So at this support, there will be one vertical reaction, one horizontal reaction, and one moment will be there. Okay, similarly at this support, there is one vertical reaction, one horizontal reaction, and one moment will be there. So total number of reactions are. So total number of reactions is basically equals to 6, right? And equilibrium equations are basically 3. What are those equations? Summation fx0, summation fy0, and summation mz0. Okay, right? So static indeterminacy of this frame will be basically equals to 6 minus of 3, that is 3. Okay. Next step is to calculate the location where the plastic hinges can form. Okay. So plastic hinges can form where there will be peak bending moments. Okay, and the peak bending moments will occur at the supports at this joints or under the point load. Okay. So there are plastic hinge can form at this A point, this B point, under this point load, at this C point. Okay. At this under this point load, okay, and again at this point, and again at this point. So total number of points are 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 places where plastic hinges can form. Plastic hinges can form. Okay, right? So basically, the purpose of calculating is this, to calculate the number of independent mechanisms. Okay, so basically the number of independent mechanism will be 7 minus of 3, that will be equals to 4. Okay, so we have calculated this. First we have calculated the static indeterminacy. Then with the help of that, we are calculating what are the number of independent mechanisms are over here. Okay, so basically, now we need to calculate. Now we will be identifying what are those mechanisms basically. Okay, so you can see that there will be 2 beam mechanisms. Okay, one mechanism can take place in this beam BC, or you can say that in this, basically this is rafter. Basically this we call rafter. One mechanism can take place in this BC member. One mechanism can take place in this CD member. Okay, so there will be 2 beam mechanism. Okay, one on member BC, one on member CD, right? Next will be our sway mechanism. Okay, next will be our sway mechanism. Okay, so 3 mechanisms are there. Now number 4 will be about these 2 mechanisms we have already discussed. This is Gable mechanism. Okay, so in Gable mechanism, what will happen? The plastic hinge, suppose this is our Gable, the plastic hinge will form like this. Okay, so it will deform something like this. So you can see that there is a flattening of gable. Okay, flattening of gable. Okay, so basically the shape of the gable is changing. So that's why this is called the gable mechanism. Okay, gable mechanism. Right? So here our main independent mechanisms will be two beam mechanisms, one sway mechanism and one this gable mechanism. Right? There should be no doubt in this. Why it is calling why we are calling it as gable mechanism? Because the shape of the gable is changing. Right? In sway mechanism, this won't take place, right? We'll see. When we'll discuss about sway mechanism, we'll see, right? So now we will be considering the beam mechanism in this BC member, okay? So if you take this BC member, okay, the plastic hinges are forming at the plastic hinge. When there is a mechanism in this BC member, the plastic hinge will form at this B point, this C point, and at this point load, okay, where this W load is acting, right? This distance is given 3.75, this is 3.75, okay. We can calculate this angle, okay. This angle will be equals to tan inverse 6 by 4.5, okay. So the value will be shift tan inverse 6 divided by 4.5, 53.13. Okay, so this angle is basically 53.13 degree, right? Now let us suppose next step you will give the virtual displacement theta. Okay, we will give the virtual displacement theta. Okay. So when you are giving the virtual displacement, how it will deflect, right? So it will deflect. This point will move perpendicular to this. So this will be our theta. Oh, sorry. This is our virtual displacement theta, and the direction is clockwise. Here also the direction is clockwise. Okay. Here also the direction is what? Direction is clockwise theta. Here also the direction is theta clockwise. Okay, so the plastic moment will act opposite to this rotation. So at the C point, the plastic moment will act like this. This will be 1.5 MP. Okay, here it will be 1 MP. At this point, it will be 1.5 MP. 1.5 MP. Right. So basically, now we will be applying the principle of virtual work to calculate collapse load. Right? So collapse load, if you want to calculate the collapse load, we will be using the concept of external virtual work done equals to internal virtual work done. Okay. So what will be our internal virtual work done? Internal virtual work done here will be at this point B, it will be MP into theta 1. Let us suppose if this displacement is theta 1. These theta are equal because this displacement is because these two distances are equal. So that's why these theta and theta will be equal, right? So this is MP into theta 1 plus. At this point, it will be 1.5 MP into theta 1, right? Plus at this point, it will be 1.5 MP into theta 1 plus 1.5 MP into theta 1. And this should be equals to external virtual work. And what will be the external virtual work? Let us write it as W into delta, because the external virtual work will be done by this W load, right? And we need to calculate what will the value of the delta. Okay, and the delta we need to consider is now when you are applying the rotation. Let us draw again here. Let us suppose this is our member. Okay, so now the plastic hinge is forming and it deflected like this, right? So this W load, this W load is acting at this point. Okay, so we need to calculate this delta basically. This is delta. not this one. Okay, we need to calculate the displacement along the load. Okay, just remember that between these 2 points, what is a vertical difference? This delta is a vertical difference between these 2 points. So work done will be W into delta. Remember that thing. Okay, understand that thing. Okay, so if this is delta, how we need to calculate this delta value basically? Okay, this angle we already calculated. This complete angle is 53.13 degree, right? If you draw a parallel line just to this angle will be also be equals to 53.13. How? Corresponding angles, right? So this angle will be 36.87. Again, this angle will be 36.87. So this delta I can write. What will be this length? What will be this thing? This is nothing but this will be equals to 3.75 theta. Okay. So delta I can write 3.75 theta. This is 3.75 theta. This displacement will be 3.75 theta. 3.75 theta into sine 36.87 degree. Okay. This displacement we can calculate because this theta is very, very small virtual displacement. So I can write 3.75 theta, this displacement, and the component of this displacement in vertical direction will be 3.75 theta into sine 36.87 degree, right? So this delta will be equals to 3.75 theta sine 36.87 degree, right? Now, this will be 3, 4.5, 5.5. So this is 5.5 MP into theta 1, okay? And this will be equals to 3.75 into sine 36.87. This is 2.25 W into theta. Theta will cancel out each other. So the value will be 5.5 divided by 2.25. So this value comes out to be 2.44 MP equals to W. Okay. So when the plastic hinges is forming in this portion, in this member, in this rafter basically, so the collapse load is coming out to be 2.44 MP. So W is equals to 2.44 MP when the collapse is taking place in the member BC, and this is basically beam mechanism. Okay, so this is not a critical one. We have to check all the cases. First for the sway, then for the Gable mechanism, then for the combined mechanism. Okay, so you cannot say that this is the answer. Okay, we need to check other mechanisms also, right? So this is the beam mechanism in this BC member. Okay, now we will be calculating what will be the collapse load when the mechanism is forming in this CD member. Guys, this is a very, very important problem. Okay, so you need to understand this problem very carefully. I don't need this now. Okay, now next case is when the mechanism is taking place in the member CD. Okay, mechanism. So when the mechanism is taking place in the member CD, the plastic hinge will form. Where the plastic hinge will form? Plastic hinge will form at this end and at this point where the load is acting. Okay, so these are our plastic hinges. Okay, so now here this W load is acting 2W. Now when you will give, let us first calculate this angle. This angle will be tan inverse 6 divided by 8, and its value comes out to be 36.86 degree. Okay, so this is 36.86 degree, right? So when you are giving the virtual displacement, again this will move perpendicular to this member, right? And these are our plastic displacement. Okay, so now the load is acting like this. Okay, so what we need to calculate? So let us suppose first you are giving the virtual displacement theta, and this is, let us suppose, theta 2. This will be also be theta 2 because this is 5 meter, this is 5 meter, right? So this I can calculate. This will be 5 into theta 2. Okay, this theta is very small, right? So at this point, this is theta 2, this is theta 2. Okay. So direction of the moment will be opposite to this theta 2. At this point, the moment will be 1.5 MP. Hinge will form in the weak member. Here also, the hinge will form in the weak member, and again, the moment will be MP. At this point, the moment will be 2 MP. Here also, the moment will be 2 MP. So the direction of the moment will be opposite to direction of the rotation, right? So again, using the principle of virtual work, I can write external work done equals to internal work done. Okay. So basically now we need to calculate which displacement. We need to calculate this delta. Okay. So let us suppose if this is our beam CD, hinge is forming like this. This is load. Now the displacement, the plastic after the collapse, after the applying the virtual displacement, our this member looks displaces in this way. Okay, so this is nothing but this is theta 1, theta 2, this is theta 2, right? So we need to calculate basically this delta. This is delta. Okay. So if you want to calculate this delta, this complete angle is 36.86. This will be also be equal to 36.86 corresponding angles. This will be 53.13. So this is 36 point. Oh, sorry. This angle will be 53.13 alternate angles. So this we know, so we can find this thing. Delta will be equals to 5 into theta 2 into again sine 53.13. Okay. Same way in which we have calculated delta which we calculated in this member. Okay. Same method we are using, right? So again, if you apply the principle of virtual work, what is external virtual work in this hinge? Sorry, internal virtual work in this hinge, at this hinge. So it will be 1.5 MP into theta 2 plus. At this location, the internal work absorbed will be MP into theta 2, right? Plus. At this point, the internal work absorbed will be 2 MP into theta 2 plus 2 MP into theta 2, right? And this will be equals to external virtual work. External virtual work will be due to this load. Okay, will be due to this load. So this will be again 2W into delta. And delta is what? Delta is what? 5 into theta 2 into sine 53.13. Right? So if you calculate this thing, this comes out to be 1.5 plus 1 plus 2, 4. Okay. This is 6.5 MP into theta 2. This should be equals to 2W into 5, 2 into 5 into sine 53.13. So this is basically 8W theta 2. Theta 2 will cancel out each other, right? So the value comes out to be 6.5 MP divided by 8. So this is W equals to 0.8125 MP. Okay. So in the previous case, we got that result W equals to 2.44 MP. Here we are getting 0.8125 MP. So the meaning of which that this is more critical than this. This case is more critical than this. Okay. So if there are two options, out of these two options, this is our design load. Okay. If there are only two options, one this, if the one beam mechanism this and one beam mechanism in this. Now out of these two, this will be critical. Okay. So this is okay. I hope there is no problem in this. Next, we are calculating the sway mechanism. Next, we are calculating the collapse load for the sway mechanism. Okay. So next we are dealing about the sway mechanism, collapse load when there is sway mechanism in this Gable frame. Okay. So this is our Gable frame. In pure sway mechanism, we have discussed that the plastic hinges will form at the top and the bottom of the columns. Okay. So one plastic hinge will form at this portion. One plastic hinge will form at this portion, one plastic hinge form at the top of this column, and one plastic hinge will form at the bottom of this column. Okay. So when you are giving it as a displacement, this portion, this joint will move perpendicular to this. Similarly, this joint will move perpendicular to this, right? Okay. And this portion will deflect like this. Okay. So this Gable portion won't deflect. Won't deflect means this angle will remain 90 degree. Initially also this angle is 90 degree. If you calculate, this angle will be 90 degree. So still this angle will remain 90 degree. Okay. So our Gable shape is intact. So that's why this is sway mechanism, not Gable mechanism. Okay. Right. So this is 90. This will remain 90. Okay. And these two deflection will be equal. This is delta 1. Let us suppose this is delta 2. So if for inextensibility, if member are inextensible, so you can write delta 1 is equals to delta 2. Okay. So this will be our case. Okay. So you can see that this deflection will be equals to this deflection. Okay. So all the members, all this joint is moving perpendicular, this portion is moving exactly horizontal. Okay. So if W load is acting at this point, similarly W load will act here. This is the position of the W load after sway. Here also, if 2W load is acting over here, again, right? So this is 2W. Okay. Here 1.5W and 0.5W. And here one W load is acting. Okay. Right. Okay, guys. So now we will be, this is okay. I hope this point is clear to you. Right. Now we will be calculating what will be the collapse load for this sway mechanism. Okay. Collapse load for this sway mechanism. Okay. So let us suppose this is theta 3. Okay. Right. This is 4 meter. This is 6 meter. Okay. So if this is theta 3, delta 1 is equals to delta 2. So what will be this theta? What will be this theta? This theta will be equals to, I can write delta 2 equals to 4 into theta 3. And let us suppose this is theta dash. So this delta 1 I can write delta 1 is equals to 6 into theta 1, theta dash. So if you equate if you equate both the equation, 4 into theta 3 equal to 6 into theta 1. Theta 1 will be here, from here will be 2 by 3 theta 3, which is equals to theta dash. This angle will equals to 2 by 3 theta. How? Because this delta 1 will be equals to this delta 2. Okay. So now this will also be vertical, horizontal, exactly horizontal. Okay. So now again will you use the concept of principle of virtual work, and we'll say the external work done will be equals to internal virtual work done. Okay. So let us first calculate what is our external virtual work done. Okay. So external virtual work done will be due to this W load, and what it will be W into what is theta over here, delta over here. It will be value of delta 1 6 into 2 by 3 theta. Okay, right? This load will not do any external virtual work done, because this is moving exactly in horizontal direction. Okay, there is no vertical deflection over here. Okay, these points are moving exactly in the same direction, right? So exactly in the horizontal direction. So no work done due to this load. Similarly, no work done will be due to this load. This 1.5 will not do any work, but external virtual work done will be due to 0.5 W plus 0.5 W. What will be this delta? This delta will be equals to again 6 into 2 by 3 theta, and this will be equals to internal virtual work done. So internal virtual work done. Okay, so at this point, this is the direction of the rotation. Okay, this point, this is straight. Okay, so MP, so here this is the direction of the rotation MP, this is MP. So at this point, first we write the work absorbed will be MP into 2 by 3 theta. At this point, work done will be MP into 2 by 3 theta, right? This angle will be equal. Okay, plus at this point there will be no work done because no plastic hinge is there. Similarly, at this point the work done will be internal virtual work done will be, this is the direction of the rotation, MP will act like this. Similarly here MP will act like this. So plus MP into this is theta 3. So this is theta 3 plus MP into theta 3. Okay, these are all theta 3. Okay, this is theta 3, right? So again, if you calculate the value from here, this will be 2, so this is 4. Again, this will be 2, 4 plus 2, this is 6 W theta 3 equals to, this is MP into, this is 2 by 3 plus 2 divided by 3 plus 2 divided by 3 plus 1 plus 1. So this is equals to 10 by 3 MP into theta 3. Okay, theta t will cancel out each other. So W from here will be 10 over 18 MP. So value of W will be 10 divided by 18. This is equals to, W equals to 0.555 MP. Okay. So the collapse load coming out for the sway mechanism is what? W equals to 0.55 MP. Okay guys. So out of these three, this one is critical, right? So guys, now we are going to calculate the collapse load for the Gable mechanism, right? So let us draw our frame. Okay, This is our frame, right? And we have discussed that the plastic hinges are forming at this point, this B point, this C point, this D point, and this E point. Okay, for Gable mechanism, 4 hinges are sufficient. There is no need of hinge to form at this A point. Okay, so 4 hinges are sufficient to make this Gable frame to form Gable mechanism, right? To form the Gable mechanism. Okay, so now let us draw the deflection shape. Okay, let us draw the deflection shape, right? So let us suppose you are applying a theta rotation at here, a virtual displacement theta over here. Okay, so when you are giving the virtual displacement theta, this joint should move perpendicular to this axis. Okay, so it will deflect like this portion. Okay, similarly, if we come at B, at A there is no plastic hinge, so this portion won't move. This portion won't move. Okay, won't move or won't deflect, right? And this joint will move perpendicular to this axis for the axial rigidity, because members are axial rigid. Okay, there should be no axial deformation, so this member will move perpendicular to this. Okay, so it will like this, it will move like this, right? And after, so this is the location of hinge. And this will be our deflected shape. Okay, so now you can see that this is perpendicular to this axis. Okay, this is perpendicular to this axis, right? This angle is 90 degree basically. Okay, so now you can see that this joint is moving with respect, is rotated about this B point. Okay, similarly this joint, or you can say that this joint is rotating about this hinge. Okay, this plastic hinge, right? So as a whole, this member, this CD member, at the end we are having some hinges, so this member as a whole will be rotating about some point. Okay, so in this lecture, not in this lecture, because in this mechanism we will be learning some new concept which is called instantaneous center method. Okay, instantaneous center method. Okay, so what we will do in this method is that basically the purpose of this method is to calculate the deflection and the rotation at the hinges. Okay, or at the desired location. Okay, to calculate rotation and deflection at hinges. Okay, it will be easy, right? So this C point, the C joint is rotating about B. This D joint is rotating about E. Okay, this is E, this is D, this is C, this is C dash, this is C, this is B, this is D dash. Okay, so as a whole this member will rotate about some point. Okay, that point we call as instantaneous center method. Okay, so now we will be locating that instantaneous center. Okay, so this joint is moving perpendicular to this. Okay, so if this member is rotating about something, if some point, so the center of rotation will lie along this axis. Okay, will lie along this axis, right? This straight line. Okay, will lie along this axis. Similarly, this joint is moving perpendicular to this D axis. Okay, so for this member, again the center of rotation will lie along this axis. Okay, so where these two axes are meeting, that point we defined as instantaneous center. Okay, as a whole, you can say that this member is rotating about this instantaneous center. Let us suppose this is O. Okay, right? So what I want to tell you that suppose this point, this joint is moving perpendicular to this. Okay, this joint is moving perpendicular to this. So its instantaneous center of this joint, of this, what you can say that of this member will lie along this axis. Okay, because this member is rotating as a whole about this center. Okay, so this point is moving straight. So its center of it should rotate like this. Okay, it should rotate like this. So its center of rotation will lie along this axis. Okay, so this is the way you locate the instantaneous center. Okay. Similarly, here also the same concept. Okay, this point is moving perpendicular to this, so instantaneous center of this member will lie along this axis. Okay, so as a whole, this member is rotating about this instantaneous center. So this is instantaneous center, right? So now, okay, so this is okay. Now, let us suppose this all is happening due to the virtual rotation theta 4 at this point. So we are giving a virtual rotation in clockwise direction and the magnitude is theta 4. Okay, right? So due to this virtual displacement, all this is happening. Okay, so now so this is okay. So now what we will do, this we will be calculating. So this distance we know. Okay, this distance is basically 12.5. Okay, up to here this is 8 and here remaining is 4.5. Okay, so let us first calculate what is the value of OD. Okay, first we are going to calculate what is the value of OD. Okay, OD, how we can calculate OD? OD is what? If you see this triangle, this complete triangle, this BOD, in triangle BOD, triangle BOD, what is the angle OBD? OBD is 53.13 degree. We have already discussed about this thing. Okay, this complete angle is 53.13 degree. So our situation is like this. This is B, this is D, and this is O. This angle is 53.13 degree, right? This distance we know is 12.5 meter. So what will be this distance? OD will be equals to tan 53.13 into 12.5. Okay. And what will be the value? The value will be tan 53.13 into 12.5. So this value comes out to be 16.66. This value comes out to be 16.667. Okay. So this OD, this distance is basically equals to 16.667, right? This is okay. And here this is C point. Okay. So now OC will equals to, and this BC is basically 7.5, which is already given. So OC will be equals to 16.667, not 16.667. OC will be equals to under root 12.5 square plus 16.667 square. Okay, so plus 12.5 square 0.5. So OC is 20.83, right? So what is the value of CO? CO will be equals to 20.83 minus 7.5. This distance BC is basically 7.5. So 20.3 minus 7.5 will give the value 13.33. OD is 16.667. This is 13.33, right? So we have calculated this is OB, this distance is 13.33. Okay. Why we are calculating this? We'll see now. So I can say that OD, let us suppose this is alpha. Okay, I can say O, first what is DD dash? DD dash will be equals to this is 4 meter, this is 6 meter. DD dash will be equals to 4 into theta 4, because theta 4 is very small. Okay. Similarly, I can say that DD dash will also be equals to OD into alpha. OD is what? 16.667 into alpha, right? So if you equate these two equations, I can write 4 theta 4 is equals to 16.667 alpha, right? So from here, I can calculate the value of alpha. So 4 divided by 16.667 will give me the value 0.24. 0.24 theta 4 is equals to alpha. So at the center O, we are giving the rotation of 0.24 theta. Okay, due to this rotation at the center, this member is rotating about this center by an angle of 0.24 theta. Okay, so this is basically 0.24 theta, 24 alpha. Okay, so this rotation is at the center. Okay, so this will also be equals to 0.24 alpha. Okay, because this rotation is generating at the center, right? This rotation is generating at the center, so 1.24 theta will be 0.24 alpha. Sorry, this is theta 4. Okay, because this member as a whole is rotating about rotating by an angle 0.24 alpha with respect to this set, rotating about with respect to this center. Okay, right? So we are giving the rotation 0.24 alpha, 0.24 theta 4, 0.24 theta 4 at this center. Okay, so this will also, because this is the rotation only now, so this will be rotated by 0.24 theta. This also will be rotated by 0.24 theta. Okay, I hope this point is clear to you, right? So now this is okay. Now what will be this angle? Let us, this is beta, because there is rotation at this rotation at the hinge, rotation for this BC member. Okay, what will be this value of this beta? Okay, so I can calculate what is CC dash. CC dash is nothing but it is equals to 13.33 into 0.24 theta 4. Okay, because this theta 4 is very small. Similarly, I can write here this is 7.5. So this CC dash is also equals to 7.5 into beta, right? So if you equate these two equations, 13.33 into 0.4 theta 4 is equals to 7.5 beta, right? From here, the value of beta comes out to be, beta is equals to 0.43. Okay, 43 theta 4. Okay, so this beta is 0.43 theta 4. Okay, so we have calculated the rotation, the rotation at the hinges, right? Now, now I can say that at this B, we are having at the B point, we are having rotation of 0.34 theta 4. Okay, only this member is rotating, this member is not rotating, so net rotation at this B point is 0.43 theta 4, right? What about at E point? At E point, it is equals to theta 4, right? I'm not bothering about direction right now. Okay, and what about C point? Okay, so this is important. So if you see, this is our case. Okay, the C member is coming here, and this is D dash, right? So if you draw a parallel line to this, this will be our angle. This angle will be beta. That will be equals to 0.4 theta 4. And direction is what is the direction? Direction is basically what you can say that it is clockwise. Okay. Similarly, if you come at this C point, okay, what will be the rotation? This is deflecting like this. Okay, this is deflecting like this, right? So you can see that this is deflecting with respect to original axis by amount 0.24 theta 4. Okay, with respect to the original axis, this will be deflecting by 0.24 theta 4. Okay, right? So this is okay. With respect to the original axis, it will deflect by 0.24, it will rotate by 0.24 theta 4. Okay, right? This is okay. This we are getting from here only. Okay, this when this member is straight, there is no rotation. There is no rotation. Okay, when this is the CD, there is no rotation. Okay, this is our instantaneous center. Now you are giving the theta rotation. It is rotating by theta 0.24 theta, 0.24 theta. So every part. So this will rotate about this. Every part will rotate about the original axis with the value 0.24 theta 4. Okay, so this angle will be 0.24 theta 4. So at C, the net rotation, these are in opposite direction, so net rotation will be 0.24 theta 4 plus what? Plus this is 0.43 theta 4. Okay. Similarly, if you come at D point, right? So this is our original axis. So let us draw the perpendicular line to parallel line to original axis. Okay. So this angle will be our, with respect to original axis, our rotation is in which direction? This is in anti-clockwise direction. So this rotation will also be anti-clockwise. So this is the rotation 0.24 theta 4. Again, you can see that this member is rotated about original axis by 0.24 theta 4. Okay. Similarly, what about this rotation? This is theta 4. So at D, again, these two rotations are opposite directions. So net rotation will be 0.24 theta 4 plus theta 4. Okay. And at D point, at E point, the rotation is theta 4, which we have already discussed. Okay. So this is how you are going to calculate the rotation at each joint. Okay. This is very, very important to understand. Okay. So this is okay. Now we are applying, we need to calculate the collapse load for this frame with the Gable mechanism. So what we need to do? We need to do is that we need to apply the principle of virtual work over here. Okay. So applying the principle of virtual work. External work done will be equals to internal work done. Okay, this is okay. So let us first calculate what will be the internal work done. So internal work done will be always at the plastic hinges only. Okay, so plastic hinges are forming at this B point, the C point, this D point and E point. So internal work done will be here only. Okay. So at B, what will be the internal work done? Internal work done will be NP, the plastic hinge will form in the weak member, NP into what is the rotation at B? This is 0.43 theta 4. You need to understand this very properly, okay? This is very, very important, right? So this mechanism basically. So at the C, the hinge will form in the weak member, so it will be 1.5 NP into C. Net rotation at C is 0.24 theta 4 plus 0.43 theta 4. This is okay, right? Similarly at D point, the plastic hinge will form in a weak member, so it will be MP into 0.24 theta 4 plus theta 4, right? Similarly at E point, it will be MP into theta 4, and this will be equals to external virtual work. External virtual work. Okay, this is internal virtual work. Why internal virtual? Why it is virtual? Because this is the virtual displacement theta 4 which you are giving, right? So due to this theta 4, there will be some virtual displacement under the loads. Okay, at the points where the load is acting. So in that way, the external virtual load concept is come from there. The external virtual load concept is coming, right? So now the important step is to calculate what is the external virtual work over here. Okay. So I hope this internal work done is clear to you. Okay. So let us draw this frame again. So when the plastic hinges are forming, so it is deflecting like this. Okay. So load is acting basically at what point? At which point? At here, this is W load. Here one W load is acting. Okay. Here 1.5 W and 0.5 W load, and here also one load is acting, which is the magnitude of which is 2 W. Okay. So this distance is basically 3.5, 3.75, 3.75. This is 3.75. Okay. This is 5. This is 5. This distance. Okay. So now let us first see, due to this load, when there is a displacement, when you are applying the virtual displacement, the frame will deflect like this. Okay. So this load, the work done will be due to this load, the load at this point, and due to this load. Okay. So now let us first come to this this point C. Okay, this point C. Okay, at C you can see that there will be one horizontal deflection. There will be one horizontal deflection and one vertical deflection. Okay, so let us suppose this horizontal deflection is delta H and this vertical deflection is delta V. So work done due to 1.5 load, 1.5 W will be 1.5 W into delta V, and the horizontal load is acting 0.5 W into delta H. You need to check the direction of the displacement. Here this point is coming down, so work done will be positive. Okay, and this point is moving forward in the direction of the load, so the work done will be positive, right? You need to check the direction also. Okay, so this is okay. So first we are going to calculate what is the value of this delta V, sorry. Okay, so delta V we need to calculate, right? So now let us come to this. Delta V need to calculate. Okay, this is very easy, right? So delta V we need to calculate. Okay, so this displacement, this we know, this we already know. This is what? This is basically 13.33 into the CC dash into 0.24 theta 4. Okay, right? This is basically CC dash. This is CC dash. Okay, so this angle is what? 53.13. This angle will be again 53.13. So this remaining angle will be what? This remaining angle, this will be 36.87. Okay, so let us suppose this angle is 36.87. So delta V I can write CC dash into sine 36.87. This is okay, right? So what is CC dash? CC dash is basically 13.33 into 0.24 theta into sine 36.87, right? So if you multiply these two terms, 13.33 into sine 36.87, this will be equals to 13.33 into sine 36.87. So this is equals to 8 into 0.24 theta. Okay, this is very important. Now we can calculate how easily we can get this expression. Okay, so here you can see that when this member is rotating about the center by 0.24 theta amount. Okay, so here what we'll do, we'll draw one line. I hope this thing is coming on my video. Okay, in frame of the video. So at this, you are drawing a parallel line to this line. Okay, right? So we need to calculate what is the vertical deflection of this point C. Okay, so from here we'll move to 8 meter distance, and we'll rotate this by 0.24 theta. Okay, so this will give me the deflection. 0.24 theta into 8. Okay, so anywhere in this member, if I want to calculate the vertical deflection at any point, I'll use this concept. I'm going to use this concept. Okay, so here you can calculate, this is 8 into 0.4 theta, this vertical deflection, right? From here again, if you use the concept of delta H, you can calculate delta H will be what? Delta H will be 13.33 into 0.24 theta into cos 36.87. This will be value of delta H. Okay, so delta H will be 13.33 into 0.24 into cos 36.87. So this value is coming out to be 2.56 theta. Okay, so we have calculated what is the value of delta V. This is 8 into 0.24 theta, and delta H will be equals to delta H is what? 2.56 theta. Okay, so this is theta 4, sorry. So again, if you want to calculate the vertical deflection for this member, okay, for any point in this member, you will use this concept. Okay. Now you can see that I got the value of this delta H and delta V. Okay. Now these two loads, why I need to calculate delta H? Because here one point load is acting in horizontal direction. If there was no horizontal load, then we don't need to calculate this delta H. Okay. Now let us come to this point. So this point, at this point again we need to calculate what is the vertical deflection when this member is rotated by 0.24 theta for amount. Okay, when this member is rotated, what is the vertical deflection will be there? Okay, because when this member is rotated, this 0.24 will shift somewhere here. Okay, somewhere here. So what is the vertical deflection basically? So what is the vertical deflection? This deflection will be, we are going to calculate. Okay, so again I'll be using the same principle here. I'm not going to calculate all these. You can calculate also by using that breaking the displacement. Here it is easy basically. If you want to calculate a deflection here, you can also calculate in the more basic way which we calculate. Okay, by breaking what you can say that using this displacement and apply the theta and those concepts, we can calculate in that manner also. But this thing is very, very simple. Okay, So now you want to calculate the displacement under this point. Okay, this load is acting at a distance 5 meter from this point. Okay, and 5 meter from this point. Okay, so again we'll be drawing one line. So from here at a distance of 5 meter, if you rotate this member by 0.24 theta, 0.24 theta 4 by 0.24 into theta 4, this will give me the vertical deflection. Okay, so this will be the value of delta V at F. Delta, let us suppose this point is F, this point is E. So delta F will be equals to delta VF will be 5 into, not 5, we need to have horizontal projection basically. What is the value of, what will be the value of this? So this is basically, this is 5. So 5 into, this is cos 36 point, this angle is 36.87. So 5 into cos 36.87. So this value is 4. Okay. So from here you need to move 4 meter distance. Okay. And this when it is rotated by 0.24 theta amount, this also will be rotated by 0.24 theta 4. Okay. This will give me the vertical deflection. Okay. So delta VF will be equals to 4 into 0.24 theta 4. Okay, so this is okay. Now again I need to calculate what will be the deflection under this point load. Okay, under this point load. So this is delta VE. Right. So now you can see that for this member, this member is rotating about this joint. Okay, this member is rotating about this joint. So what we'll do, we'll extend this line. Okay, and again the load is acting at this point. This is 3.75. We'll take the projection. Projection is what? 3.75 into sine. This is cos 53.13. So this value is 2.25. So again, from here, let us suppose we'll be moving. This is 2.25, and we'll move by what theta at this member is rotated by at what angle? What was the angle? 0.43 theta 4. 0.43 theta 4. So vertical deflection will be 2.25 into 0.43 theta 4. Okay, because this member is not rotating about this joint. Okay, that's why we are not taking this distance from here. Okay, this member is rotating about this, but you can say that this B joint. Okay, so this is how you calculate the vertical deflection under the point load. If you use the what you can say that you can also calculate by break. Suppose at this point you can calculate the deflection, this displacement. Then again use that, break the displacement into x and y direction. That is a little bit cumbersome. Okay, so this method is very easy. Okay, this method is very easy. If you do that by that method, then also this thing will come. Okay, so this is okay. So external work will be equals to, at this point I can write it will be 1.5 W into 8 into 0.24 theta 4. Right, no doubt should be in this. Okay, at due to 0.5 load, 0.5 W into 2.56 theta 4. Okay, plus again at this F point it will be 2 W into 4 into 0.24 theta 4, plus at this E point it will be W into 2.25 into 0.43 theta 4. Okay, so due to this load W, there will be no work done because this joint is not moving in a horizontal direction. Okay, so this is the very important thing to understand, how we derive this expression. Okay, this is very important, right? So now first we will be calculating what is the value of the internal work done, then what is the value of external work done, total value, then we will be calculating the value of W, right? So this will be 0.43 plus 1.5 into 0.24 plus 0.43 plus 1.24 plus 1. So this is 3.675 MP into theta 4. And this should be equals to, what is the value of this expression? So 1.5 into 8 into 0.24 plus 0.5 into 2.56 plus 2 into 4 into 0.24 plus 2.25 into 0.43. So this value comes out to be 7.0475 W theta 4. Theta 4 will cancel out each other, right? So this is 3.675 divided by this value will give me the value 0.521 W MP is equals to W, right? So what is the value of W when there is Gable mechanism? The value is 0.521 MP, okay, when there is Gable mechanism. Okay, Gable mechanism. Okay, so I hope this point is clear to you. We learned different things in this problem, like instantaneous center, how to calculate the deflection under the point load in easy method. Okay, in easy method, right? So this is okay. I hope this problem, I hope this point, the thing which I want to tell is clear to you. Still, if you have any doubt, you can write in the comment sections. Okay. And in the next lecture, we are going to use the concept of combined mechanism, where we will be going to find the critical values. Okay. So up to this four mechanism, out of this four mechanism, this mechanism is critical one. Okay. Right. So